Class 12 NCERT Unit 2 Electrochemistry. Electrochemistry is the study of production of electricity from energy released during spontaneous chemical reactions and the use of electrical energy to bring about non-spontaneous chemical transformations. The subject is of importance both for theoretical and practical considerations. A large number of metals, sodium hydroxide, chlorine, fluorine, and many other chemicals are produced by electrochemical methods. Batteries and fuel cells convert chemical energy into electrical energy and are used on a large scale in various instruments and devices. The reactions carried out electrochemically can be energy efficient and less polluting. Therefore, study of electrochemistry is important for creating new technologies that are eco-friendly. The transmission of sensory signals through cells to brain and vice versa and communication between the cells are known to have electrochemical origin. Electrochemistry is therefore a very vast and interdisciplinary subject. In this unit, we will cover only some of its important elementary aspects. 2.1 Electrochemical cells. We have studied the construction and functioning of Daniell cell. The cell converts the chemical energy liberated during the redox reaction. That is, zinc plus Cu2 positive gives out Zn2 positive plus copper to electrical energy and has an electrical potential equal to 1.1 volt when concentration of Zn2 positive and Cu2 positive ions is unity. Such a device is called a galvanic or a voltaic cell. If an external opposite potential is applied in the galvanic cell and increased slowly, we find that the reaction continues to take place till the opposing voltage reaches the value 1.1 volt. When the reaction stops altogether and no current flows through the cell, any further increase in the external potential again starts the reaction but in the opposite direction. It now functions as an electrolytic cell, a device for using electrical energy to carry non-spontaneous chemical reactions. Both types of cells are quite important and we shall study some of their silent features in the following pages. 2.2 Galvanic cells. As mentioned earlier, a galvanic cell is an electrochemical cell that converts the chemical energy of a spontaneous redox reaction into electrical energy. In this device, the Gibbs energy of the spontaneous redox reaction is converted into electrical work which may be used for running a motor or other electrical gadgets like heater, fan, geyser, etc. Daniell cell discussed earlier is one such cell in which the following redox reaction occurs. Zn plus Cu2 positive gives Zn2 positive plus Cu. This reaction is a combination of two half reactions whose addition gives the overall cell reaction. First, Cu2 positive plus 2 electron gives Cu. Second, Zn gives Zn2 positive plus 2 electron. These reactions occur in two different portions of Daniell cell. The reduction half reaction occurs on the copper electrode while the oxidation half reaction occurs on the zinc electrode. These two portions of the cell are also called half cells or redox couples. The copper electrode may be called the reduction half cell and the zinc electrode the oxidation half cell. We can construct innumerable number of galvanic cells on pattern of Daniell cell by taking combinations of different half cells. Each half cell consists of a metallic electrode dipped into an electrolyte. The two half cells are connected by a metallic wire through a voltmeter and a switch externally. The electrolytes of the two half cells are connected internally through a salt bridge as shown in figure 2.1. Sometimes both the electrode dips in the same electrolyte solution and in such cases we do not require a salt bridge. At each electrode electrolyte interface, there is a tendency of metal ions from the solution to deposit on the metal electrode, trying to make it positively charged. At the same time, metal atoms of the electrode have a tendency to go into the solution as ions and leave behind the electrons at the electrode, trying to make it negatively charged. At equilibrium, there is a separation of charges, and depending on the tendencies of the two opposing reactions, the electrode may be positively or negatively charged with respect to the solution. A potential difference develops between the electrode and the electrolyte, which is called electrode potential. When the concentrations of all the species involved in a half cell is unity, then the electrode potential is known as standard electrode potential. According to IUPAC convention, standard reduction potentials are now called standard electrode potentials. In a galvanic cell, the half cell in which oxidation takes place is called anode, and it has a negative potential with respect to the solution. The other half cell in which reduction takes place is called cathode, and it has a positive potential with respect to the solution. Thus, there exists a potential difference between the two electrodes, and as soon as the switch is in the on position, the electrons flow from negative electrode to positive electrode. The direction of current flow is opposite to that of electron flow. The potential difference between the two electrodes of a galvanic cell is called the cell potential and is measured in volts. The cell potential is the difference between the electrode potential of the cathode and anode. It is called the cell electromotive force of the cell when no current is thrown through the cell. It is now an accepted convention that we keep the anode on the left and the cathode on right while representing the galvanic cell. A galvanic cell is generally represented by putting a vertical line between metal and electrolyte solution and putting a double vertical line between the two electrolytes connected by a salt bridge. Under this convention, the EMF of the cell is positive and is given by potential of the half cell on the right hand side minus the potential of the half cell on the left hand side, that is, E cell is equal to E right minus E left. This is illustrated by the following example. Cell reaction Cu plus 2Ag positive gives Cu2 positive plus 2Ag. Half cell reactions cathode reduction gives 2Ag positive plus 2 electron, that is 2Ag. Anode oxidation Cu gives out Cu2 positive plus 2 electron. It can be seen that the sum of 3.5 and 3.6 leads to overall reaction 2.4 in the cell, and that silver electrode acts as a cathode and copper electrode acts as an anode. The cell can be represented as Cu2 positive aqueous salt bridge, Ag positive and Ag solid, and we have E cell is equal to E right minus E left. The potential of individual half cell cannot be measured. We can measure only the difference between the two half cell potentials that gives the EMF of the cell. If we arbitrarily choose the potential of one electrode, then that of the other can be determined with respect to this. According to convention, a half cell called standard hydrogen electrode represented by PTS H2G H positive aqueous is assigned a zero potential at all temperatures corresponding to the reaction H positive plus electron gives 1 half H2. The standard hydrogen electrode consists of a platinum electrode coated with platinum black. The electrode is dipped in an acidic solution and pure hydrogen gas is bubbled through it. The concentration of both the reduced and oxidized forms of hydrogen is maintained at unity. This implies that the pressure of hydrogen gas is 1 bar and the concentration of hydrogen ion in the solution is 1 molar. At 298 Kelvin, the EMF of the cell, standard hydrogen electrode, second half cell constructed by taking standard hydrogen electrode as anode and the other half cell as cathode, gives the reduction potential of the other half cell. If the concentrations of the oxidized and the reduced forms of the species in the right hand half cell are unity, then the cell potential is equal to standard electrode potential E naught R of the given half cell. E naught is equal to E naught right minus E naught left. As E naught left for standard hydrogen electrode is 0, so E naught is equal to E naught right. The measured EMF of the cell is 0.34 volt, and it is also called the value for the standard electrode potential of the half cell corresponding to the reaction Cu2 positive plus 2 electron gives Cu. Similarly, the measured EMF of the cell is minus 0.76 volt corresponding to the standard electrode potential of the half cell reaction Zn2 positive aqueous 1 molar plus 2 electron gives Zn. The positive value of the standard electrode potential in the first case indicates that Cu2 positive ions get reduced more easily than H positive ions. The reverse process cannot occur, that is, hydrogen ions cannot oxidize copper, or alternatively we can say that hydrogen gas can reduce copper ion under the standard conditions described above. Thus, copper does not dissolve in HCl. In nitric acid, it is oxidized by nitrate ion and not by hydrogen ion. The negative value of the standard electrode potential in the second case indicates that hydrogen ions can oxidize zinc, or zinc can reduce hydrogen ions. In the view of this convention, the half cell reaction for the Daniell cell in figure 2.1 can be written as left electrode Zn gives out Zn2 positive aqueous 1 molar plus 2 electron. Right electrode copper 2 positive plus 2 electron gives Cu. The overall reaction of the cell is the sum of above two reactions, and we obtain the equation Zn plus Cu2 positive gives out Zn2 positive plus copper. EMF of the cell E naught cell is equal to E naught right minus E naught left, that is 0.34 volt plus 0.676 volt gives 1.10 volt. Sometimes metal like platinum or gold are used as inert electrodes. They do not participate in the reaction but provide their surface for oxidation or reduction reactions and for the conduction of electrons. For example, platinum is used in the following half cells: hydrogen electrode Pt, H2 and H positive. With half cell reaction, H positive plus electron gives half H2. Bromine electrode Pt as Br2 aqueous, Br negative aqueous. With half cell reaction, half Br2 aqueous plus electron gives Br negative. The standard electrode potentials are very important and we can extract a lot of useful information from them. The values of standard electrode potentials for some selected half cell reduction reactions are given in table 2.1. If the standard electrode potential of an electrode is greater than 0, then its reduced form is more stable compared to hydrogen gas. Similarly, if the standard electrode potential is negative, then hydrogen gas is more stable than the reduced form of the species. It can be seen that the standard electrode potential for fluorine is the highest in table, indicating that fluorine gas has the maximum tendency to get reduced to fluoride ions, and therefore fluorine gas is the strongest oxidizing agent and fluoride ion is the weakest reducing agent. Lithium has the lowest electrode potential, indicating that lithium ion is the weakest oxidizing agent, while lithium metal is the most powerful reducing agent in an aqueous solution. It may be seen that as we go from top to bottom in table 2.1, the standard electrode potential decreases, and with this decreases the oxidizing power of the species on the left and increasing the reduces power of the species on the right hand side of the reaction. Electrochemical cells are extensively used for determining the pH of solutions, solubility product, equilibrium constant and other thermodynamic properties, and for potentiometric titrations. 2.3 Nernst equation. We have assumed in the previous section that the concentration of all the species involved in the electrode reaction is unity. This need not be always true, Nernst showed that for the electrode reaction, Mn positive plus an E electron gives M. The electrode potential at any concentration measured with respect to standard hydrogen electrode can be represented by E Mn positive to M gives out equal to E naught Mn positive M minus RT by NF ln of concentration of M by concentration of Mn positive. But concentration of solid M is taken as unity, and we have E naught Mn positive M has already been defined. R is gas constant, F is Faraday constant, T is temperature in Kelvin, and Mn positive is the concentration of the species Mn positive. Table 2.1. Ions are present as aqueous species and water as liquid. Gases and solids are shown by G and S. In Daniell cell, the electrode potential for any concentration of Cu2 positive and Zn2 positive ions, we write for cathode E Cu2 positive to Cu gives equal to E naught Cu2 positive Cu minus RT by 2F into ln of 1 by Cu2 positive aqueous. For anode, E of Zn2 positive to Zn equal to E naught of Zn2 positive to Zn minus RT by 2F into ln of 1 by Zn2 positive aqueous. The cell potential is E cell equal to E of Cu2 positive to copper minus E of Zn2 positive to Zn. That is, E cell is equal to E naught cell minus RT by 2F into ln of concentration of Zn2 positive by concentration of Cu2 positive. It can be seen that E cell depends on the concentration of both Cu2 positive and Zn2 positive ion. It increases with the increase in concentration of Cu2 positive ions and decreases with the concentration of Zn2 positive ion. By converting the natural logarithm in equation 2.11 to the base 10 and substituting the values of R, F and T equal to 298 Kelvin, it reduces to E cell is equal to E naught cell minus 0.059 by 2 into log of Zn2 positive by Cu2 positive. We should use the same number of electrons for both the electrodes, and thus for the following cell, the cell reaction is Ni plus 2 Ag positive gives Ni2 positive plus 2 Ag. The Nernst equation can be written as E cell is equal to E naught cell minus RT by 2F into ln of Ni2 positive by Ag positive whole square. And for a general electrochemical reaction of the type AA plus BB gives out an E electrode Cc plus Gd. Nernst equation can be written as E cell is equal to E naught cell minus RT by NF into ln of Q equal to E naught cell minus RT by NF into ln of concentration of C raised to the power C, concentration of D raised to the power D, concentration of A raised to the stoichiometric coefficient A into concentration of B raised to power B. 2.3.1 Equilibrium constant from Nernst equation. If the circuit in Daniell cell is closed and we note that the reaction Zn plus Cu2 positive gives out Zn2 positive plus copper takes place as time passes, the concentration of Zn2 positive keeps on increasing while the concentration of Cu2 positive keeps on decreasing. At the same time, voltage of the cell as read on the voltmeter keeps on decreasing. After some time, we shall note that there is no change in the concentration of Cu2 positive and Zn2 positive ions, and at the same time, voltmeter gives zero reading. This indicates that equilibrium has been attained. In this situation, the Nernst equation may be written as E cell is equal to 0 equal to E naught cell minus 2.303 RT by 2F into log of Zn2 positive by Cu2 positive, or E cell is equal to 2.303 RT by 2F into log of Zn2 positive by Cu2 positive. But at equilibrium, Zn2 positive by Cu2 positive is equal to Kc, and at T equal to 298 Kelvin, the above reaction can be written as E naught cell is equal to 0.059 volt by 2 into log of Kc is equal to 1.1 volt. Log Kc is equal to 37.288. Kc is equal to 2 into 10 to the power 37 at 298 Kelvin. In general, A naught cell is equal to 2.303 RT by NF into log of Kc. Thus, the above equation gives a relationship between equilibrium constant of the reaction and standard potential of the cell in which that reaction takes place. Thus, equilibrium constants of the reaction, difficult to measure otherwise, can be calculated from the corresponding A naught value of the cell. 3.2.3.2 Electrochemical cell and Gibbs energy of the reaction. Electrical work done in 1 second is equal to electrical potential multiplied by total charge passed. If we want to obtain maximum work from a galvanic cell, then charge has to be passed reversibly. The reversible work done by a galvanic cell is equal to decrease in its Gibbs energy, and therefore if the EMF of the cell is E and NF is the amount of charge passed and delta Rg is the Gibbs energy of the reaction, then delta G is equal to minus NF E cell. It may be remembered that E cell is an intensive parameter, but Gibbs energy of reaction is an extensive thermodynamic property and the value depends on N. Thus, if we write the reaction Zn plus Cu2 positive gives out Zn2 positive plus Cu, so Gibbs energy for reaction is equal to minus 2F E cell. But when we write the reaction 2Zn plus 2Cu2 positive gives out 2Zn2 positive plus 2Cu, so Gibbs free energy is equal to minus 4F E cell. If the concentration of all the reacting species is unity, then E cell is equal to E naught cell, and we have delta Rg naught is equal to minus NF E naught cell. Thus, from the measurement of E naught cell, we can obtain an important thermodynamic quantity, delta Rg naught, standard Gibbs energy of the reaction. From the later, we can calculate equilibrium constant by the equation delta Rg naught is equal to minus Rt into ln of K. 2.4 Conductance of electrolytic solutions. It is necessary to define a few terms before we consider the subject of conductance of electricity through electrolytic solutions. The electrical resistance is represented by the symbol R and it is measured in ohm, which in terms of SI base unit is equal to kg meter square by S cube A square. It can be measured with the help of a Wheatstone bridge with which you are familiar from your study of physics. The electrical resistance of any object is directly proportional to its length L and inversely proportional to its area of cross section A. That is, R is directly proportional to L by A, or R is equal to rho L by A. The constant of proportionality rho is called resistivity. Its SI unit are ohm meter and quite often its sub-multiple ohm centimeter is also used. IUPAC recommends the use of the term resistivity over specific resistance, and hence in the rest of the book we shall use the term resistivity. Physically, the resistivity for a substance is its resistance when it is 1 meter long and its area of cross section is 1 meter square. It can be seen that 1 ohm meter is equal to 100 ohm centimeter, or 1 ohm centimeter is equal to 0.01 ohm meter. The inverse of resistance R is called conductance G, and we have the relation G is equal to 1 by R equal to A by rho L equal to K into A by L. The SI unit of conductance is Siemens, represented by the symbol S and is equal to ohm inverse or mho. The inverse of resistivity called conductivity is represented by the symbol kappa. IUPAC has recommended the use of term conductivity over specific conductance, and hence we shall use the term conductivity in the rest of the book. The SI unit of conductivity are Simon per meter, but quite often kappa is expressed in Simon per centimeter. Conductivity of a material in Simon per meter is its conductance when it is 1 meter long and its area of cross section is 1 meter square. It may be noted that 1 Simon per centimeter is equal to 100 Simon per meter. It can be seen from table 2.2 that the magnitude of conductivity varies a great deal and depends on the nature of the material. It also depends on the temperature and pressure at which the measurements are made. Materials are classified into conductors, insulators, and semiconductors depending on the magnitude of their conductivity. Metals and their alloys have very low conductivity and are known as conductors. Certain known metals like carbon black, graphite, and some organic polymers are also electronically conducting. Substances like gas, ceramics, etc. have been very low conductivity are known as insulators. Substances like silicon, doped silicon, and gallium arsenide having conductivity between conductors and insulators are called semiconductors and are important electronic materials. Certain materials called superconductors by definition having zero resistivity or infinite conductivity. Earlier, only metals and their alloys at very low temperatures were known to behave as superconductors, but nowadays a number of ceramic materials and mixed oxides are also known to show superconductivity at temperatures as high as 150 Kelvin. Electrical conductance through metals is called metallic or electronic conductance and is due to the movement of electrons. The electronic conductance depends on first, the nature and structure of the metal, second, the number of valence electrons per atom, third, temperature. As the electrons enter at one end and go out through the other end, the composition of the metallic conductor remains unchanged. The mechanism of conductance through semiconductors is more complex. We already know that even pure water has a small amount of hydrogen and hydroxyl ions which lend it very low conductivity. When electrolytes are dissolved in water, they furnish their own ions in the solution and hence its conductivity also increases. The conductance of electricity by ions present in the solution is called electrolytic or ionic conductance. The conductivity of electrolytic solution depends on first, the nature of the electrolyte added, second, size of the ions produced and their dissolution, third, the nature of the solvent and its viscosity, fourth, concentration of the electrolyte, fifth, temperature. Passage of direct current through ionic solution over a prolonged period can lead to change in its composition due to electrochemical reactions. 2.4.1 Measurement of the conductivity of ionic solutions. We know that accurate measurements of an unknown resistance can be performed on a Wheatstone bridge. However, for measuring the resistance of an ionic solution, we face two problems. Firstly, passing direct current changes the composition of the solution. Secondly, a solution cannot be connected to the bridge like a metallic wire or other solid conductor. The first difficulty is resolved by using an alternating current source of power. The second problem is solved by using a specifically designed vessel called conductivity cell. It is available in several designs and two simple ones are shown in figure 2.4. Basically, it consists of two platinum electrodes coated with platinum black. Finely divided metallic platinum is deposited on the electrodes electrochemically. These have area of cross section equal to A and are separated by distance L. Therefore, solution confined between these electrodes is a column of length L and area of cross section A. The resistance of such a column of solution is then given by the equation R is equal to rho into L by A, that is equal to L by kappa A. The quantity L by A is called cell constant, denoted by the symbol G star. It depends on the distance between the electrodes and their area of cross section and has the dimension of length inverse and can be calculated if we know L and A. Measurement of L and A is not only inconvenient but also unreliable. The cell constant is usually determined by measuring the resistance of the cell containing a solution whose conductivity is already known. For this purpose, we generally use KCl solutions whose conductivity is known accurately at various concentrations and at different temperatures. The cell constant G star is then given by the equation G star is equal to L by A equal to R kappa. Once the cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. The setup for the measurement of the resistance is shown in figure 2.5. It consists of two resistance R3 and R4, a variable resistance R1 and the conductivity cell having the unknown resistance R2. The Wheatstone bridge is fed by an oscillator or source of AC power in the audio frequency range. P is a suitable detector, a headphone or other electronic device, and the bridge is balanced when no current passes through the detector. Under these conditions, unknown resistance R2 is equal to R1 into R4 by R3. These days, inexpensive conductivity meters are available which can directly read the conductance or resistance of the solution in the conductivity cell. Once the cell constant and the resistance of the solution in the cell is determined, the conductivity of the solution is given by the equation kappa is equal to cell constant by R is equal to G star by R. The conductivity of solutions of different electrolytes in the same solvent and at a given temperature differs due to charge and size of the ions in which they dissociate, the concentration of ions or ease with which the ions move under a potential gradient. It therefore becomes necessary to define a physically more meaningful quantity called molar conductivity, denoted by the symbol lambda m. It is related to the conductivity of the solution by the equation molar conductivity is equal to lambda m is equal to kappa by C. In the above equation, if kappa is expressed in Simon per meter and the concentration C in mole m minus 3, then the unit of lambda m are in Simon meter square per mole. It may be noted that 1 mole by meter cube is equal to 1000 into molarity, and hence lambda m is equal to kappa by 1000 liter per meter cube into molarity. If we use Simon per centimeter as the units for kappa and mole per centimeter cube the units of concentration, then the units for lambda m are Simon centimeter square per mole. It can be calculated by using the equation lambda m is equal to kappa into 1000 by molarity. Both type of units are used in literature and are related to each other by the equation 1 Simon meter square per mole is equal to 10 to the power 4 Simon centimeter square per mole, or 1 Simon centimeter square per mole is equal to 10 to the power minus 4 Simon meter square per mole. 2.4.2 Variation of conductivity and molar conductivity with concentration. Both conductivity and molar conductivity change with the concentration of the electrolyte. Conductivity always decreases with decrease in concentration both for weak and strong electrolytes. This can be explained by the fact that the number of ions per unit volume that carry the current in a solution decreases on dilution. The conductivity of a solution at any given concentration is the conductance of 1 unit volume of solution capped between two platinum electrodes with unit area of cross section and a distance of unit length. This is clear from the equation G is equal to kappa into A by L equal to kappa. Both A and L are unity in their appropriate units in meter or centimeter. Molar conductivity of a solution at a given concentration is the conductance of the volume V of solution containing 1 mole of electrolyte capped between two electrodes with area of cross section A and distance of unit length. Therefore, lambda m is equal to kappa into A by L equal to kappa. Since L equal to 1 and A is equal to V, volume containing 1 mole of electrolyte, lambda m is equal to kappa into V. Molar conductivity increases with the decrease in concentration. This is because the total volume V of solution containing 1 mole of electrolyte also increases. It has been found that decrease in kappa on dilution of a solution is more than compensated by increase in its volume. Physically, it means that at a given concentration, lambda m can be defined as the conductance of the electrolytic solution capped between the electrodes of a conductivity cell at unit distance but having area of cross section large enough to accommodate sufficient volume of solution that contains 1 mole of the electrolyte. When concentration approaches zero, the molar conductivity is known as limiting molar conductivity and is represented by the symbol lambda m naught. The variation in lambda m with concentration is different for strong and weak electrolytes. Strong electrolytes. For strong electrolytes, lambda m increases slowly with dilution and can be represented by the equation lambda m is equal to lambda m naught minus A under root C. It can be seen that if we plot lambda m against under root C, we obtain a straight line with intercept equal to lambda m naught and slope equal to minus A. The value of the constant A for a given solvent and temperature depends on the type of electrolyte, that is, the charges on the cation and anion produced on dissociation of the electrolyte in the solution. Thus, NaCl, CaCl2, MgSO4 are known as 1,1, 2,1 and 2,2 electrolytes respectively. All electrolytes of a particular type have the same value for A. Kohlraasch examined lambda naught values for a number of strong electrolytes and observed certain regularities. He noted that the difference in lambda m naught of the electrolyte NaX and Kx for NaX is nearly constant. For example, at 298 Kelvin, lambda m naught KCl is minus lambda m naught NaCl is equal to lambda m naught KBr minus lambda m naught NaBr, equal to lambda m naught Ki minus lambda m naught Nai equal to 23.4, and similarly it was found that lambda naught NaBr minus lambda naught NaCl equal to lambda naught KBr minus lambda naught KCl approximately 1.8 Simon per centimeter square per mole. On the basis of above observation, he enunciated Kohlraasch law of independent migration of ions. The law states that limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. Thus, if lambda naught Na positive and lambda naught Cl negative are limiting molar conductivity of sodium and chloride ion respectively, then the limiting molar conductivity for sodium chloride is given by the equation lambda naught NaCl is equal to lambda naught Na positive plus lambda naught Cl negative. In general, if an electrolyte on dissociation gives nu positive cation and nu negative anion, then its limiting molar conductivity is given by lambda naught is equal to mu naught plus lambda positive naught plus nu naught minus lambda negative naught. Here lambda positive naught and lambda negative naught are the limiting molar conductivities of the cation and anion respectively, and the values of lambda naught for some cations and anion at 298 Kelvin are given in table 2.4. Weak electrolytes. Weak electrolytes like acetic acid have lower degree of dissociation at higher concentrations, and hence for such electrolytes the change in lambda m with dilution is due to increase in the degree of dissociation, and consequently the number of ions in total volume of solution that contains 1 mole of electrolyte. In such cases, lambda m increases steeply on dilution, especially near lower concentration. Therefore, lambda n naught cannot be obtained by extrapolation of lambda m at zero concentration. At infinite dilution, electrolyte dissociates completely, but at such low concentration, the conductivity of the solution is so low that it cannot be measured accurately. Therefore, lambda m naught for weak electrolytes is obtained by using Kohlraasch law of independent migration of ions. At any concentration C, if alpha is the degree of dissociation, that it can be approximated to the ratio of molar conductivity lambda m at the concentration C to limiting molar conductivity lambda m naught. Thus, we have alpha is equal to lambda m by lambda m naught. But we know that for a weak electrolyte like acetic acid, Ka is equal to C lambda square by lambda m naught into lambda m naught minus lambda m. Applications of Kohlraasch law. Using Kohlraasch law of independent migration of ions, it is possible to calculate lambda m naught for any electrolyte from the lambda naught of individual ions. Moreover, for weak electrolytes like acetic acid, it is possible to determine the value of its dissociation constant once we know the lambda m naught and lambda m at a given concentration C. 2.5 Electrolytic cells and electrolysis. In an electrolytic cell, external source of voltage is used to bring about a chemical reaction. The electrochemical processes are of great importance in the laboratory and the chemical industry. One of the simplest electrolytic cell consists of two copper strips dipping in an aqueous solution of copper sulfate. If a DC voltage is applied to the two electrodes, then Cu2 positive ions discharge at the cathode and the following reaction takes place. Cu2 positive plus 2 electron gives Cu. Copper metal is deposited on the cathode. At the anode, copper is converted into Cu2 positive ions by the reaction. Cu gives out Cu2 positive plus 2 electron. Thus, copper is dissolved at anode and deposited at cathode. This is the basis for an industrial process in which impure copper is converted into copper of high purity. The impure copper is made an anode that dissolves on passing current, and pure copper is deposited at the cathode. Many metals like sodium, magnesium, aluminium, etc. are produced on large scale by electrochemical reduction of their positive cations, where no suitable chemical reducing agents are available for this purpose. Sodium and magnesium metals are produced by the electrolysis of their fused chlorides, and aluminium is produced by electrolysis of aluminium oxide in presence of cryolite. Quantitative aspects of electrolysis. Michael Faraday was the first scientist who described the quantitative aspects of electrolysis. Now, Faraday's law also flows from what has been discussed earlier. Faraday's law of electrolysis. After his extensive investigation of electrolysis of solution and melts of electrolytes, Faraday published his result during 1833-34 in the form of the following well-known Faraday's two laws of electrolysis. First law: the amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte or solution or melt. Second law: The amounts of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. Atomic mass of metal divide number of electrons required to reduce the cation. There were no constant current available during Faraday's time. The general practice was to put a calorimeter, a standard electrolytic cell, for determining the quantity of electricity passed from the amount of metal, generally silver or copper, deposited or consumed. However, Colo- colometers are now obsolete and we now have constant current I sources available, and the quantity of electricity Q passed is given by Q is equal to IT. Q is in coulombs where I is in amperes and T is in second. The amount of electricity required for oxidation or reduction depends on the stoichiometry of the electrode reaction. For example, in the reaction Ag positive plus electron gives Ag. 1 mole of the electron is required for the reduction of 1 mole of silver ion. We know that charge on one electron is equal to 1.6021 into 10 की power minus 19 coulomb. Therefore, the charge on 1 mole of electron is equal to Na into 1.6021 into 10 to power minus 19 coulomb equal to 6.02 into 10 की power 23 per mole into 1.6021 into 10 to power minus 19. C is equal to 96487 coulomb per mole. This quantity of electricity is called Faraday and is represented by the symbol F. For approximate calculation, we use 1 Faraday equal to 96500 coulomb per mole. For the electrode reactions, Mg2 positive plus 2 electron gives Mg solid. Al3 positive plus 3 electron give Al solid. It is obvious that 1 mole of Mg2 positive and Al3 positive require 2 mole of electrons and 3 mole of electrons respectively. The charge passed through the electrolytic cell during electrolysis is equal to the product of current in amperes and the time in seconds. In commercial production of metals, current as high as 50,000 amperes are used that amounts to about 0.518 Faraday per second. 2.5.1 Product of electrolysis. Product of electrolysis depend on the nature of material being electrolyzed and the type of electrodes being used. If the electrode is inert, it does not participate in the chemical reaction and acts only as source or sink for electrons. On the other hand, if the electrode is reactive, it participates in the electrode reaction. Thus, the product of electrolysis may be different for reactive and inert electrodes. The product of electrolysis depend on different oxidizing and reducing species present in the electrolytic cell and their standard electrode potentials. Moreover, some of the electrochemical processes, although feasible, are so slow kinetically that at lower voltage these do not seem to take place and extra potential called overpotential has to be applied, which makes such process more difficult to occur. For example, if we use molten NaCl, the products of electrolysis are sodium metal and chlorine gas. Here we have only one cation Na positive which is reduced at the cathode and one anion Cl negative which is oxidized at the anode. During the electrolysis of aqueous sodium chloride solution, the products are NaOH, Cl2 and H2. In this case, besides Na positive and Cl negative ions, we also have H positive and OH negative ion along with the solvent molecule water. At the cathode, there is competition between the following reduction reaction. Na positive plus 1 electron give Na and H positive plus 1 electron gives half H2. The reaction with higher value of E naught is preferred and therefore the reaction at the cathode during electrolysis is H positive plus electron gives half H2. But H positive is produced by the dissociation of water, that is water in liquid form gives H positive aqueous plus OH negative aqueous. Therefore, the net reaction at cathode may be written as the sum of 2.33 and 2.34, and we have H2O water in liquid plus electron gives half H2 gas plus OH negative. At the anode, the following oxidation reactions are possible. Cl negative aqueous gives half Cl2 gas plus electron, and E node cell is equal to 1.36 volt, and 2 water liquid gives out O2 gas plus 4H positive aqueous plus 4 electron, and anode cell is equal to 1.23 volt. The reaction at anode with lower value of E naught is preferred, and therefore water should get oxidized in preference to Cl negative aqueous. However, on account of overpotential of oxygen, reaction 2.36 is preferred. Thus, the net reaction may be summarized as NaCl on hydrolysis gives Na positive plus Cl negative. At cathode, water plus electron gives half H2 plus OH negative. At anode, Cl negative gives half Cl2 gas plus electron. Net reaction NaCl plus water gives Na positive, OH negative plus half H2 gas plus half Cl2 gas. The standard electrode potentials are replaced by electrode potential given by Nernst equation to take into account the concentration effect. During the electrolysis of sulfuric acid, the following processes are possible at anode. 2 water molecules gives O2 plus 4H positive plus 4 electron, and E node cell is equal to 1.23 volt. 2SO4 2 negative gives out S2O8 2 negative plus 2 electron, and E node cell is equal to 1.96 volt. For dilute sulfuric acid, reaction is preferred, but at higher concentration of sulfuric acid, reaction is preferred. 2.6 batteries. Any battery, actually it may have one or more than one cell connected in series, or cell that we use as a source of electrical energy, is basically a galvanic cell where the chemical energy of redox reaction is converted into electrical energy. However, for a battery to be of practical use, it should be reasonably light, compact, and its voltage should not vary appreciably during its use. There are mainly two types of batteries. In the primary batteries, the reaction occurs only once, and after use over a period of time, battery becomes dead and cannot be reused again. The most familiar example of this type is tri-cell, known as Lelenge cell after its discovery, which is used commonly in our transistors and clocks. The cell consists of a zinc container that also acts as anode, and the cathode is a carbon rod surrounded by powdered manganese dioxide and carbon. The space between the electrode is filled by a moist paste of ammonium chloride and zinc chloride. The electrode reactions are complex, but they can be written approximately as follows. At anode, Zn gives out Zn2 positive plus 2 electron. At cathode, MnO2 plus NH4 positive plus electron gives out MnOOH plus ammonia. In the reaction at cathode, manganese is reduced from the plus 4 oxidation state to the plus 3 state. Ammonia produced in the reaction forms a complex with Zn2 positive to give ZnNH3 4 2 positive. The cell has a potential of nearly 1.5 volt. Mercury cells suitable for low current devices like hearing aids, watches, etc. consist of zinc mercury amalgam as anode and a paste of HgO and carbon as the cathode. The electrolyte is a paste of KOH and ZnO. The electrode reactions for the cell are given below. At anode, Zn plus 2 OH negative gives out ZnO plus water plus 2 electron. At cathode, HgO plus water plus 2 electron gives out Hg plus 2 OH negative. The overall reaction is represented by Zn of Hg plus HgO gives out ZnO plus Hg. The cell potential is approximately 1.35 volt and remains constant during its life as the overall reaction does not involve any ion in solution whose concentration can change during its lifetime. 2.6.2 Secondary batteries. A secondary cell after use can be recharged by passing current through it in opposite direction so that it can be used again. A good secondary cell can undergo a large number of discharging and charging cycles. The most important secondary cell is the lead storage batteries commonly used in automobiles and inverters. It consists of a lead anode and a grid of lead packed with lead dioxide as cathode. A 38% solution of sulfuric acid is used as an electrolyte. The cell reactions when the battery is in use are given below. At anode, Pb plus SO4 2 negative aqueous gives out PbSO4 plus 2 electron. At cathode, PbO2 plus SO4 2 negative plus 4H positive plus 2 electron gives out PbSO4 plus 2 water. That is, overall cell reaction consisting of cathode and anode reaction is Pb plus PbO2 plus 2H2SO4 gives out 2 PbSO4 plus 2 water. On charging the battery, the reaction is reversed and PbSO4 on anode and cathode is converted into Pb and PbO2 respectively. Another important secondary cell is nickel cadmium cell, which has longer life than the lead storage cell but more expensive to manufacture. We shall not go in details of working of the cell and the electrode reactions during charging and discharging. The overall reaction during discharge is CD plus 2NiOH whole thrice gives out CDO plus 2NiOH whole twice plus water. Product 2.7 Fuel cells. Production of electricity by thermal plants is not a very efficient method and is a major source of pollution. In such plants, the chemical energy, heat of combustion of fossil fuels, coal, gas, or oil is first used for converting water into high pressure steam. This is then used to run a turbine to produce electricity. We know that a galvanic cell directly converts chemical energy into electrical and is highly efficient. It is now possible to make such cells in which reactants are fed continuously to the electrodes and products are removed continuously from the electrolyte compartment. Galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy are called fuel cells. One of the most successful fuel cells uses the reaction of hydrogen with oxygen to form water. The cell was used for providing electrical energy in the Apollo space program. The water vapor produced during the reaction were condensed and added to the drinking water supply for the astronauts. In the cell, hydrogen and oxygen are bubbled through porous carbon electrodes into concentrated aqueous sodium hydroxide solution. Catalysts like finely divided platinum or palladium metal are incorporated into the electrodes for increasing the rate of electrode reaction. The electrode reactions are given below. At cathode, O2 gas plus 2 water plus 4 electron gives out 4 OH negative aqueous. At anode, 2H2 gas plus 4 OH negative aqueous gives out 4 water liquid plus 4 electron. Overall reaction being 2H2 gas plus O2 gas gives out 2 water molecules. The cell runs continuously as long as the reactants are supplied. Fuel cells produce electricity with an efficiency of about 70% compared to thermal plants whose efficiency is about 40%. There has been tremendous progress in the development of new electrode materials, better catalysts, and electrolytes for increasing the efficiency of fuel cells. These have been made in automobiles or an experimental basis. Fuel cells are pollution free, and in view of their future importance, a variety of fuel cells can be fabricated and tried. Corrosion slowly coats the surface of metallic objects with oxides or other salts of metal. The rusting of iron, tarnishing of silver, development of green coating on copper and bronze are some of examples of corrosion. It causes enormous damage to buildings, bridges, ships, and to all objects made of metal, especially that of iron. We lose crores of rupees every year on account of corrosion. In corrosion, a metal is oxidized by a loss of electron to oxygen and formation of oxides. Corrosion of iron, commonly known as rusting, occurs in presence of water and air. The chemistry of corrosion is quite complex, but it may be considered essentially an electrochemical phenomenon. At a particular spot of an object made of iron, oxidation takes place and that spot behaves as anode, and we can write the reaction at anode. 2Fe gives out 2Fe2 positive plus 4 electron. Anode Fe2 positive Fe gives equal to minus 0.44 volt. Electron released at anodic spot move through the metal and go to another spot on the metal and reduce oxygen in presence of H positive, which is believed to be available from H2CO3 formed due to dissolution of carbon dioxide from air into water. Hydrogen ion in water may also be available due to dissolution of other acidic oxides from the atmosphere. This spot behaves as cathode with the reaction. At cathode, O2 plus 4H positive plus 4 electron gives out 2 water, and E naught of H positive O2 H2O equal to plus 1.23 volt. The overall reaction being 2Fe plus O2 plus 4H positive gives out 2Fe positive plus 2 water. E naught cell is equal to 1.67 volt. The ferrous ions are further oxidized by atmospheric oxygen to ferric ions, which comes out as rust in the form of hydrated ferric oxide and with further production of hydrogen ion. Prevention of corrosion is of prime importance. It not only saves money but also helps in preventing accidents such as bridge collapse or failure of a key component due to corrosion. One of the simplest methods of preventing corrosion is to prevent the surface of metallic object to come in contact with atmosphere. This can be done by covering the surface with paint or by some chemicals. Another simple method is to cover the surface by other metals that are inert or react to save the object. An electrochemical method is to provide a sacrificial electrode of another metal which corrodes itself but saves the object. The hydrogen economy. At present, the main source of energy that is driving our economy is fossil fuels such as coals, oil, and gas. As more people on planet aspire to improve their standard of living, their energy requirement will increase. In fact, the per capita consumption of energy used is a measure of development. Of course, it is assumed that energy is used for productive purpose and not merely wasted. We are already aware that carbon dioxide produced by the combustion of fossil fuel is resulting in the greenhouse effect. This is leading to a rise in temperature of Earth's surface, causing polar ice to melt and ocean levels to rise. This will flood low-lying areas along the coast, and some island nations such as Maldives face total submergence. In order to avoid such a catastrophe, we need to limit our use of carbonaceous fuel. Hydrogen provides an ideal alternative as its combustion results in water only. Hydrogen production must come from splitting water using solar energy. Therefore, hydrogen can be used as a renewable and non-polluting source of energy. This is the vision of the hydrogen economy. Both the production of hydrogen by electrolysis of water and hydrogen combustion in a fuel cell will be important in future, and both these technologies are based on electrochemical principles. Summary: an electrochemical cell consists of two metallic electrodes dipping in electrolytic solution. Thus, an important component of electrochemical cell is the ionic conductor or electrolyte. Electrochemical cells are of two types. In galvanic cell, the chemical energy of a spontaneous redox reaction is converted into electrical work, whereas in an electrolytic cell, electrical energy is used to carry out a non-spontaneous redox reaction. The standard electrode potential for any electrode dipping in an appropriate solution is defined with respect to standard electrode potential of hydrogen electrode taken as 0. The standard potential of the cell can be obtained by taking the difference of standard potentials of cathode and anode. E naught cell is equal to E naught cathode minus E naught anode. The standard potential of cells are related to standard Gibbs energy and equilibrium constant of the reaction taking place in the cell. Concentration dependence of the potential of the electrodes and the cells are given by Nernst equation. The conductivity kappa of an electrolytic solution depends on the concentration of the electrolyte, nature of solvent and temperature. Molar conductivity lambda m is defined by kappa by C, where C is concentration. Conductivity decreases but molar conductivity increases with the decrease in concentration. It increases slowly with decrease in concentration for strong electrolyte, while the increase is very steep for weak electrolyte in very dilute solution. Kohlraasch found that molar conductivity at infinite dilution for an electrolyte is the sum of contribution of the molar conductivity of ions in which it dissociates. It is known as law of independent migration of ions and has many applications. Ions conduct electricity through the solution, but oxidation and reduction of the ions take place at electrodes in an electrochemical cell. Batteries and fuel cells are very useful forms of galvanic cell. Corrosion of metal is essentially an electrochemical phenomena. Electrochemical principles are relevant to the hydrogen economy. Thank you.